The change of variable formula. Okay, so let's move on to a crucial part of mastering integration by substitution. As you recall from the previous section, we've been exploring integration by substitution, a powerful technique for tackling more complex integrals. Now, to really become proficient with this method, it's not enough to just know how to do the steps. We need to understand why those steps work. That's where the concept we're diving into today comes in. We need to understand the underlying mathematical principle that justifies changing from one variable to another within an integral. This fundamental principle, the reason substitution works, is what we call the change of variable formula. Think of it as the engine that drives the entire substitution process. We'll be building on this formula in the coming slides, so it's important to grasp it firmly. We'll be looking at the derivation, applying it with examples, and even discussing common pitfalls to avoid. So, let's begin by solidifying our understanding of this core formula. Understanding the concept. Okay, let's move on to slide 2. Now, in the previous slide, we introduced the change of variable formula, and we talked about why we need it to make integration easier. This slide explains how it connects to something you've already learned, the chain rule. So, the first point here states that integration by is essentially the inverse process of the chain rule in differentiation. Think about it like this. Differentiation and integration are like opposite operations, they undo each other. And substitution, which we're learning now, is deeply linked to how the chain rule works in reverse. Now, you'll remember that in differentiation, the chain rule allows us to find the derivative of a composite function. What do I mean by a composite function? Well, it's a function inside another function, like, for example, sine of x squared. The chain rule tells us how to find the rate of change of that entire function, taking into account the rates of change of both the outer and inner functions. In integration, the change of variable formula, which is what we're building up to, allows us to simplify a complex integral by replacing a part of the expression we're integrating, which we call the integrand, with a new variable. It's like strategically choosing a substitution to untangle a complicated integral. And finally, this transformation, this substitution we make, converts the integral into a standard form that is easier to solve. We aim to get to an integral that we immediately recognize how to solve, using our basic integration rules. We'll see this in action on the next slide with a concrete example. But the key takeaway here is that the change of variable formula isn't just a trick. It's fundamentally connected to the chain rule, and it's about cleverly simplifying the integral to make it solvable. The mathematical derivation. Point 1. The substitution first. Let's start with a general integral. Integral of f of x with respect to x, we represent this mathematically as integral f of x dx. Now the core idea is to replace our original variable, x, with a new variable, t. We don't just pick t randomly, though. We define a relationship between x and t using a differentiable function, which we'll call g of t. This means we say x equals g of t. Think of g as a transformation function that converts t into x. Point 2, the differential change. Now, this is where things get a little subtle. Because x is now defined in terms of t, we can't simply swap dx for dt. That would be incorrect. Remember, dx represents an infinitesimally small change in x, and dt represents an infinitesimally small change in t. They aren't directly interchangeable. We need to figure out how these changes relate to each other. To do this, we use differentiation. We differentiate x with to t, which gives us dx over dt equals g prime of t. G prime of t is just the derivative of the function g with respect to t. This tells us the rate at which x changes as t changes. Point 3, expressing dx. Now that we have the relationship between the rates of change, we can express dx in terms of dt. We simply rearrange the equation from the previous step. Multiplying both sides by dt, we get dx equals g prime of t dt. This is a crucial step. This equation tells us exactly how a small change in t corresponds to a small change in x. Point 4, the final transformation. Finally, we can perform the substitution into our original integral. we replace both x with g of t and dx with g prime of t dt. This gives us a new integral of f of g of t multiplied by g prime of t with respect to dt. We can write this as integral f of g of t, g prime of t dt. This entire equation, integral f of x dx equals integral f of g of t, g prime of t dt, is the change of variable formula. It's important to understand that this formula isn't just about replacing x with t. It's about correctly accounting for how the infinitesimally small changes in the variables relate to each other. That g prime of t term, that's the scaling factor that ensures the value of the integral remains unchanged even though we've switched variables. We'll see how this scaling factor works in practice on the next slide with an example, and we'll also discuss common mistakes to avoid. Okay, so let's dive into the mathematical derivation of the change of variable formula. As we discussed on the previous slide, this formula is deeply connected to the chain rule from differentiation, and it's crucial for making integration by substitution work correctly. Real-world analogy, currency conversion. Okay, so we've established the change of variable formula, and we saw how it's derived from the chain rule. Now, let's build some intuition about why we need that extra factor, that g prime of t, what we're calling the scaling factor, when we change variables. This slide uses a real-world analogy to help us grasp this concept. Think about currency conversion. Imagine you're figuring out the total cost of some items, and those items are priced in US dollars, which we're representing with the variable x. But let's say you want to do all your calculations, the summation, in Indian rupees, which we'll call t. Now, you can't just magically swap the dollar sign for the rupee symbol. That would be incorrect. You can't simply replace one currency with another without accounting for their relative values. You must multiply every value expressed in dollars by the exchange rate to get the equivalent value in rupees. The exchange rate is the key. It's the factor that allows you to accurately convert between the two currencies. It's the differential that ensures the total value, the overall cost, remains the same, even though you've changed the units. For example, let's say $1 is equal to 83 Indian rupees. That's written as 1 USD equals 83 INR. 83, in this case, is our exchange rate. It's the scaling factor that bridges the gap between dollars and rupees. Similarly, in calculus, that g prime of t, the derivative of our substitution function, acts as that exchange rate. It's the scaling factor that bridges the gap between the variable x and the variable t. It ensures that when we change variables in our integral, we don't alter the overall value of the integral itself. So remember that g prime of t isn't just some mathematical formality. It's essential for maintaining the integrity of the calculation when we switch from one variable to another. We'll see this in action as we work through more examples, like the one on the next slide. Step-by-step example. Okay, let's solidify our understanding of the change of variable formula with a step-by-step example. As we discussed in the previous slides, this is all about strategically simplifying integrals. Here, we want to solve the integral of 2x times cosine of x squared with respect to x. I'll write that as integral 2x cosine of x squared dx. Remember, the goal is to make this integral easier to handle. Step 1, identify the substitution. Now, the key is to spot a good substitution. Look closely at the integrand, the function inside the integral. We notice that x squared is a function within another function, cosine. This is our inner function. And importantly, the derivative of x squared, which is 2x, is already present in the integral. That's a big clue, so we're going to let x squared equal t. Step 2, find the differential dx. All right, we've made our substitution. T equals x squared. But remember from our earlier discussion, we can't just swap x for t. We need to account for how the infinitesimally small changes in x relate to changes in t. That's where the differential comes in. We need to find dx in terms of dt. So we differentiate both sides of our substitution, t equals x squared. With respect to x, this gives us dt by dx equals 2x. Now, to isolate dx, we rearrange this equation. Dividing both sides by 2x, we get dx equals dt divided by 2x. This is crucial. It's our scaling factor, our exchange rate, as we discussed with the currency analogy. Step 3. Substitute into the integral. Now we can perform the substitution. We replace every instance of x squared with t, and we replace dx with dt divided by 2x. This transforms our original integral into integral of 2x times cosine of t times dt divided by 2x. Step 4. Simplify the expression. Look what happens next. Notice that we have a 2x in the numerator and a 2x in the denominator. These cancel each other out, beautifully simplifying the integral to just integral of cosine of t dt. See how choosing the right substitution can dramatically simplify things. Step 5. Integrate with respect to t $. Now we have a much simpler integral. The integral of cosine of t with respect to t is a standard result. Sine of t plus a constant, so our integral becomes sine of t plus c. Step 6. Substitute back the original variable. We're almost there. Remember, we want our final answer in terms of the original variable. X, we made the substitution t equals x squared, so we need to substitute that back in. Replacing t with x squared, we get sine of x squared plus c, and there you have it. We've successfully solved the integral using the change of variable formula. This is a powerful technique, and with practice, you'll become proficient at spotting the right substitutions and applying the formula effectively. In the next slide, we'll discuss some common mistakes to avoid, so you can be even more confident in your integration skills. Common mistakes to avoid. Okay, let's move on to slide 6. This slide highlights some common pitfalls students encounter when applying the change of variable formula or integration by substitution, which we've been discussing. Paying attention to these will save you a lot of frustration. 1. Forgetting the differential. This is by far the most frequent mistake I see. Remember, when we're making a substitution, let's say we replace x with g of t, we can't just change the x part of the integral. The dx also needs to be transformed. What we saw on the previous slides is that dx becomes g prime of t dt. So, if you simply replace x with t and ignore the dx part, you're not correctly accounting for the scaling factor, and your integration will be incorrect. Let's look at the example provided. If you have the integral of cosine of x squared dx, and you incorrectly substitute just to get the integral of cosine of t dt, you've made a mistake. The correct approach, as we've learned, is to find what dx is in terms of dt and include that factor in your integral. 2. Incorrect back substitution. Now, after you've successfully integrated with respect to your new variable, t, it's crucial to express your answer in terms of the original variable, x. It's surprisingly common for students to stop after integrating with respect to t and leave the answer as a function of t. Remember, the problem was originally stated in terms of x, so your final answer must also be in terms of x. We did this in our example on slide 5. We substituted back to get our final answer in terms of x. Don't skip this step. 3. Wrong choice of substitution. Finally, let's talk about choosing the right substitution. This is where a little bit of intuition comes in, but it's also something you'll get better at with practice. If you pick a substitution where the derivative of that substitution isn't actually present in the original integral, you're likely to make things more complicated, not simpler. Think about it, the whole point of substitution is to simplify the integral. If your substitution doesn't help with that, it's probably not a good choice. We want to look for an inner function and its derivative within the integrand, as we did in the example on slide 5. So, keep these 3 common mistakes in mind as you practice. We'll now move on to slide 7, where we'll recap the key takeaways from this section. Key takeaways. Okay, let's recap everything we've learned about the change of variable formula. This slide summarizes the key takeaways, so pay close attention. First point, the change of variable formula is fundamentally the integral equivalent of the chain rule we learned in differentiation. Remember how the chain rule helped us differentiate composite functions? Well, this formula does the reverse. It helps us integrate them. It's a beautiful connection between differentiation and integration. Next, if we decide to substitute our variable x with a new variable t, defined by the function g of t, meaning x equals g of t, then it's crucial to remember that the differential also changes. We can't just replace dx with dt. Instead, the differential dx transforms into g prime of t multiplied by dt. G prime of t represents the derivative of the function g with respect to t. This is where many students make mistakes, so really internalize this step. Now let's look at the general formula. We have the integral of f of x with respect to x, which is equal to the integral of f of g of t multiplied by g prime of t with respect to t, so it looks like this. Integral of f of x dx equals integral of f of g of t, g prime of t dt. This formula encapsulates the entire process of changing variables within an integral. Finally, let's break down the process itself. It's a 5-step procedure. First, we perform the substitution, where we define our new variable and the relationship between x and t. Then, we move on to differential calculation, finding how dx relates to dt. After that, we do the transformation, replacing x and dx in the original integral with their equivalents in terms of t. Then comes the integration, solving the simplified integral with respect to t. And lastly, we perform back substitution, replacing t with x to express the final answer in terms of the original variable. Keep these steps in mind, and you'll be well equipped to tackle integration by substitution problems. In the next section, we'll practice more examples to solidify your understanding.